Hello, my name is Giulia Costa. I'm from Rome Tor Vergata University, and today I have the pleasure to present you some of the results we are obtaining regarding the leaching behavior of products from the treatment of the mineral fraction of bottom ash in full-scale plants. So first, I would like to thank the organizers of this important event for allowing me to participate with my contribution, and also the core workers of this study, both from my home university, also from ChemService, a laboratory that carries out wide range of tests, in particular ecotoxicological ones, and Adwea, Ambiente, that is a company that manages many waste management plants in Italy, including 8 large waste-to-energy plants. So waste-to-energy in Europe is a quite consolidated technology with around 500 plants treating globally around 100 million tons. Now, waste-to-energy can be seen not only as an energy recovery technology, but more and more also as part of the circular economy. And this is related in particular to the possibility of recovering various materials from the main byproduct of this treatment, bottom ash. Around 20 million tons are produced yearly in Europe, and it presents a ferrous metal content of around 10% and lower content, but still significant, of aluminum and other metals that can be recovered. But the main fraction, the mineral fraction, is being recovered also. Here I'm reporting some pictures from a large-scale plant in the Netherlands, but recently also in northern Italy, several large-scale bottom ash treatment plants have started to operate to recover metals, but also the mineral fraction. For the mineral fraction, different options are applied in Europe, going from using it only in landfills as a construction material, or instead as a road subbase layer, or as aggregates in bound or unbound applications, and even as a raw material in cement production. It has been used for several years, but recently also in ceramics manufacturing. Now, looking at the recovery rate per country, we see large differences. Overall in Europe, slightly more than 50% of the bottom ash mineral fraction is recovered, mostly in countries such as Netherlands, Denmark, and UK, but also in Italy and France. It is more and more recovered. In other countries, instead, due to the concern on the potential environmental problems of using these materials, it is not. So looking at possible barriers for recovery of the mineral fraction of bottom ash, we can recall the leaching of several elements ranging from metals to metalloids and salts, the presence of salts like chloride that can be a problem in bound applications, particularly for concrete, and different treatments can be applied depending on the intended application, ranging from washing to natural or accelerated stabilization, and use of even binders and additives. Now, looking at the situation in Italy, as I said, bottom ash is being increasingly treated in large-scale plants to recover primarily metals, but also the mineral fractions that are of different particle size ranges and can be used as aggregates or sand substitutes but only generally in bound applications, or if not, in cement or ceramics manufacturing. Different treatments are applied to the mineral fractions at these plants, ranging from size separation to crushing, in some cases, washing. Generally, natural weathering is applied in heaps. And in one of the cases we analyzed, cement is added as a binder. Now, in Italy, the recovery of these materials, their reuse in construction, is not specifically regulated, and end of waste criteria have not been issued. Therefore, utilization is decided by local authorities on a case by case basis. Generally, they make reference to compliance leaching test data using guideline values that really have been established for other materials more than 20 years ago, such as steel slag. And in some cases, they refer to results of ecotoxicity tests. Now, this type of context makes it uncertain for companies to operate, and also waste to energy plants that generate the bottom ash. They would like to have a clear idea on the utilization potential of the material and the regulation requirements. Therefore, it is necessary to develop a procedure for assessing that in an objective manner that these products don't cause negative impacts on the environment and human health. And this is the approach that Adwea Ambiente is trying to implement. And as I said, it's one of the main generators of bottom ash. And the idea is to have a full characterization of these treatment products, looking not only at the technical performance, which is typically assessed by the users or product manufacturers, but also at potential environmental aspects, characterizing fully the leaching behavior, applying different types of tests, and evaluating the results of these tests by risk assessment. On the other hand, also aquatic and terrestrial ecotoxicity tests are being carried out. And the results of these tests and the procedure are being regularly discussed with environmental protection agencies. So we are in this project involved in particular in the leaching tests, in performing them and also interpreting the results of these tests in order to identify what are the main mechanisms that govern the release, and then develop the risk analysis procedure to evaluate which are the risks for groundwater protection in conservative scenarios. So, as I said, the final aim is to develop a procedure to apply in order to evaluate the utilization potential of these products. Now, here are the 10 samples that we have been testing, and they come from 4 different plants. You see the letter here, and they present different particle size fractions and are employed in different uses. For example, sample 3 and sample 6 are employed only for cement or ceramics production, whereas instead samples 3, 4, 9, and 10 only for aggregates of different particle size fractions. The other samples are employed alternatively, either as aggregates or in cement or ceramics manufacturing. Here are some pictures. So the first 3 come from sample A, and these materials are generally the finer ones that we've analyzed, especially the first 2. The third one is used only in cement manufacturing. Here are the samples from plant B. So you see an aggregate such as sand or gravel. And similarly, also plant D produces a fine aggregate and a coarser one. Instead, plant C produces 3 samples. The first One, sample 6, is used only in cement manufacturing and contains an addition of marlstone. The other two are used also as aggregate. And in sample 7, cement is added. Now, these samples were taken from these plants in 3 different times of the year. And on each sample, chemical analysis was performed. Then leaching tests were carried out. Full characterization ones only on the first sampling, compliance leaching ones to all 3 samplings. Ecotoxicological tests are being applied to all 3 samplings, looking at aquatic organisms and terrestrial organisms. And risk assessment is being applied on the results of leaching tests. Looking at these, as I said, we're performing both characterization ones. So the first one is the upflow percolation test that investigates release as a function of a liquid to solid ratio, whereas the second type of test is pH dependence test, where different individual batch tests are performed, adding different amounts of acids or base to obtain a specific pH value of the eluate. And then the eluate is analyzed. Compliance leaching test, the N124572, is applied, the one relevant for Italy, for waste management. And then a full characterization of the eluates is carried out, looking both at major and trace contaminants, including salts, pH, dissolved organic carbon, and electroconductivity. So this is a picture of the percolation test setup that we have been using that has actually been donated to us from TNO, and thank Dr. Van Zameren directly. And in this, so here we are able to carry out 6 tests in parallel, and in each test we use around 700 grams of sample and obtain 7 liters of leachate in the end, and around half we analyze and half we send for the ecotoxicity tests. Now here are some of the results of the tests we have been performing. So we see the results for all 10 samples, the average values for some specific elements, reported as a function, so the concentration in each eluate as a function of the liquid to solid ratio. So we can see that basically the first eluates of the percolation test are the ones that contain a higher concentration of elements, which tends to decrease for larger liquid to solid ratios. And let's say it can decrease by various orders of magnitude, looking at copper, or less looking at zinc. We see a larger variety here in the case for chromium, where samples from plant C show the lowest release, whereas the ones from plant A and the coarser one of plant B shows a higher release. This is interesting to evaluate the pH. So the pH of a percolation test leachates went from 13 to around 9, and generally decreases until a liquid to solid ratio of 2, and then sort of stabilizes. Highest values were found for the sample in which cement was added. Then we can also plot the results of the percolation test as a function of the milligrams of element that are accumulated, released in, and accumulated as a function of the liquid to solid ratio. So we see that basically, again, for some elements, samples of plant C, for example, sample 6 show a higher release looking at copper or zinc. And this is interesting because similar profiles are found also for dissolved organic carbon. And we know that typically these elements, these metals, are linked to complex with dissolved organic carbon. For chlorides, generally the finer fractions tend to release more, as you can see here. And the same we can also observe for antimony and chromium over time. Here, the liquid to solid ratio. Now, looking at the results of a pH dependence test, here we plot the concentration of each element measured in the leachate as a function of pH. So we find the solubility curves that may vary very significantly with pH by various orders of magnitude, as we well know for zinc, lead, for example, but even chromium. Chromium has a typical shape of related to chromium-6. Then we see instead chlorides don't change, particularly with pH, and we see the samples that leach more. It is interesting to note that also antimony, the shape of the antimony curve is quite similar for most samples, except for sample 7, where cement is added. Now, if you want to compare these results of the pH dependence test to those reported in the literature for bottom ash of worldwide origin, so before treatment, we reported in a previous study and also results of our previous investigations on other types of mineral fractions, we see that these samples are very much in line with average bottom ash behavior, both for copper and zinc. For chromium, we're sort of a bit the upper bound of the average values, especially looking at sample 4. Then for antimony, again, it is quite similar to always in the high range, let's say, of the values reported in the literature for bottom ash, except for these lower values at alkaline pH. So here to better analyze what the two types of characterization tests tell us, we can see, for example, for aluminum, that we have coherent results from the two tests showing that at alkaline pH, aluminum is much less released by the sample with cement, and this we see also from the percolation test. Instead, for barium and lead, we see the opposite. So we find a different solubility curve and a higher release as a function of liquid to solid ratio that can be ascribed to the presence of these elements in the cement that is used, or the effect of the cement. So you can see for the whole pH range for lead, and also higher release with liquid to solid ratio. Now, for molybdenum, we don't see that effect of the cement, but we see that the same samples that show the highest release at alkaline pH coherently show the highest release also from the percolation tests. Now, we can also use the results, plot them together, actually, the results of these two characterization tests, also with the compliance leaching test, if we plot the concentrations in milligrams per liter as a function of pH. So here you see the red triangles are the results of the percolation test as a function of pH. We can distinguish two general behaviors. So, for example, aluminum, for which the results of a percolation test are quite similar to those of the pH dependence test at that pH. Same for compliance. So here really release is governed by solubility and hence pH. Whereas instead in for other elements, for example, chloride, we see that leaching from the percolation test changes by orders of magnitude and doesn't match results of pH dependence. Same also for molybdenum, DOC. And so here we can correlate the release of these constituents more to the total availability of these elements. So we are doing these evaluations for all of the samples that we tested, but the idea is also not only to understand the effects of the treatment conditions on solubility or availability mechanisms, but also how to use these results to estimate then in a reuse scenario, what is the concentration that we can expect in the groundwater, so at the point of compliance. Now, we are considering conservative use as unbound material, so not considering the presence of a binder. And in the final use, which I said in Italy is mostly bound, and using the results of both types of tests. So actually, we're making various hypotheses looking at more conservative scenarios where no dilution can be hypothesized, so direct contact of the material with groundwater, to more realistic conditions in which we assume that there's an attenuation factor in the unsaturated zone and also dilution in groundwater. So then through risk assessment, we can estimate, so back calculate protective concentrations for the groundwater that can, so guideline values that can be, therefore, we can use these to back calculate the maximum concentrations that we can tolerate in the materials used in these different scenarios. So this is what we're doing currently for risk assessment. Instead, for toxicological tests, I just reported briefly the tests that are being performed both for aquatic organisms, acute and chronic. Same as for waste classification, but here they're testing different dilutions to find the minimum dilution that doesn't bring hazardous effects on the tested organisms, and then terrestrial tests performed again with specific organisms, testing different concentrations for the ground samples, and only for the samples though that are used as aggregates. So these are still ongoing testing and elaboration, but we hope to come up also with a tiered approach that allows to perform simplified, let's say, tests, just compliance or total content, to carry out a screening, and then, if necessary, perform the characterization tests. So for further information, please refer to my email. And I thank you very much for your kind attention.